Okay, great. Let's keep going. So as I hinted yesterday, we're kind of at the midpoint, and we did all this hard preparatory work, and now we can start sort of flying down the other side of the roller coaster. And so what I want to do today will roughly correspond to steps 1 to 4 from this outline that Lucas gave in lecture 1. Okay, but we'll fill in some details of what happened there. Okay, so let's fix the usual notations. Let me fix G over F, which will be quasi-split forever. And I want to fix T and B in G. And it's B. I also want to pick a psi, so this will be a Whittaker datum. And let me just remind you what the goal of these steps 1 to 4 was. This was to construct this sequence of functors, right? A and then C and then L and then R, and kind of try to prove that they have good properties and sort of do what they are expected to do. We can't do this for arbitrary groups. We have to impose some rather severe assumptions on our sort of understanding of what's going on for this group. And so I made up some vocabulary which I hope is indicative. So definition, I'll be a little informal, but I'll try to say it precisely out loud. So G is well understood if there exists a BG basic local Langlands correspondence in the classical sense. So this will be some map from the disjoint union over B, BG basic, irreps of GBF. Towards L parameters for G, and I need this for G and all of its standard levies. So because I fixed T and B, I can talk about standard levies. And I want this to have, so this will be some map. Pi goes to phi pi with, let me just say, I'll write just good properties and say out loud what I want. So with good properties. So in particular, like finite fibers, say expected parameterization of discrete series and supracuspidal L packets. You need a little bit more. I mean, of course, we're precise in the paper about what exactly you need. And I also need that this correspondence is compatible with Farg-Schulze, so I want that the semi-simplification of this true parameter agrees with the Farg-Schulze parameter of pi. Okay? So this is a rather imposing set of conditions. So intuitively, I'm just saying we know classical local Langlands for the group. It's in good shape, and it matches Farg-Schulze up to forgetting monodromy, okay? And so this includes GLN. I'm not going to list all the names. There's about 900 people involved in verifying this for all the groups that I'll list, okay? But this includes GLN, quasi-split, classical groups, type A, B, G. D gets an asterisk for a reason I'll tell you in a second. It also includes GSP4. Products of these, and maybe some other groups. So if you're ambitious, maybe you can check that SLN is well understood. Type D gets an asterisk because in this ... I hid something technical. So I need, in particular, the endoscopic character identities for discrete series L packets for the group G and all its standard levies, okay? And in type D, this is only known up to some outer automorphism ambiguity, but it turns out that's good enough for our purposes. So I leave type D here on the list, but it gets a little asterisk. Any questions about this definition? So again, I'm not listing all the references because that would take the whole lecture, but please trust me that like this list of groups is rather well populated. Okay, so what can you get from this? So proposition, easy proposition. So if G is well understood, I'll abbreviate this to WU, like Lucas did. Then pi goes to phi pi fs, has finite fibers. Then this functor A size, remember this was this thing we act spectrally on the Whittaker representation. This preserves compact objects. And its right adjoint, therefore, which was the C size, this is right adjoint to acting on Whittaker, so this is colimit preserving. And it's QCO par G linear. Okay? And this, I'll just say out loud roughly what's happening in the proof, because this is not very difficult. Why does the FS map have finite fibers? It's because good properties, as I vaguely indicated here, includes that these true LLC maps have finite fibers, and when you semi-simplify a true parameter, there's only finitely many things that you're forgetting, only finitely many capital N's. So that part's pretty straightforward, because we're giving ourselves too much. Why does A psi preserve compact objects? So A psi is defined as this spectral action on Whittaker, right? What's the only thing that can go wrong? The only thing that can go wrong is if I have a perfect complex with quasi-compact support, you can ask sort of how many different like Bernstein blocks of GLN have the property that when you hit the Whittaker rep with the idempotent for that block, it somehow lives, it meets the support of this perfect complex, right? A priori, the map from like idempotents from like connected components of the Bernstein variety to connected components of the spectral Bernstein variety could have infinite fibers, okay? And so this somehow means that you might accidentally get something really big if you hit Whittaker with like a perfect complex with quasi-compact support. But exactly because I'm imposing finite fibers, this can't happen, okay? And there's also a theorem here that I'm using, which is, I guess, a pretty old theorem, which is that if you project Whittaker to any Bernstein block, you get something that's projective, in particular a finitely generated representation. Okay, so that's that. And then the last bit about C psi is completely formal, because right adjoint to something that preserves compacts is colimit preserving, and it's QCO par G linear because QCO par G is rigid monoidal. Okay, so that is not very substantial, but it's already a start. So we have some decent properties of these functors. To go further, we'll need to do something with Eisenstein series. But before I introduce hypotheses along those lines, let me do something unconditional. So this is a bit deeper. So let me recall from this paper I wrote with Linus and Peter. So there exists a decomposition. No, that's not what I want. So there exists a canonical decomposition, G of 1G. This is unconditional. G is any quasi-split group here. It doesn't have to be well understood into two parts, which I'll label D of Bungie I's. And so what is this? This is the stuff generated by Eisenstein functors, where P runs over proper parabolics. We'd say proper standard parabolics. So it's everything you can get from sheaves on Bun M for standard levies by applying Eisenstein series and then mashing these together however you like, okay? And then there's a complementary part, which we label D Bun G cusp. And this is the intersection of the kernels of all the constant term functors. And same indexing set, proper standard, okay? So it's actually formal from the definitions of these Eisenstein and constant term functors that these give a semi-orthogonal decomposition. And it's not so formal that, in fact, it's an orthogonal decomposition, but that really is true, okay? And by the way, you can iterate this statement if you want, because here I'm inducing from stuff on levies, but there I will have a decomposition again of this form. And so you can think that if you put all this together, this says that all of D of Bungie is generated by sort of the cuspidal part of D of bun M under Eisenstein series as you vary over all standard levies. Okay, so this is a little bit analogous to this Bernstein theory that we saw last week. Let me really say canonical orthogonal decomposition. There's another one given to us because this parameter stack is a disjoint union of two pieces, namely the locus of supercuspidal parameters, which I'll also synonymously call irreducible parameters, and then the reducible ones. So this gives me a pair of idempotents E red. In global functions on the parameter stack, which remember we were just calling this spectral Bernstein center. And this acts on everything on bun G, right? This maps to the center of the category bun G. So it acts on the identity functor, it acts on every object compatibly with all maps between all objects. And so then you get another decomposition into the stuff which morally has spectral support in the supercuspidal locus, and then the stuff that has spectral support in the sort of reducible locus. So this is a second orthogonal decomposition. Okay? Questions about these definitions? Yes?
Why do you need standout?
I don't know. It makes my psychology more comfortable. You could say all parabolics, but somehow once I fix a Borel, there's no reason not to say standard, right? Because all this somehow only depends on P up to conjugacy, and everything's conjugate to a standard parabolic. So yeah, you don't have to say standard. You can just say proper parabolics. Other questions? Yeah?
So this is not the same thing as cuspidal sheaves?
Yeah, this is an unfortunate clash of terminology. This is strictly smaller. Okay. We never used, yesterday in the afternoon, no one ever used the word cuspidal on the automorphic side, right? So there's not actually a clash, but there is a confusion perhaps. Okay, so what I'm labeling D of bun G cusp is strictly smaller than stuff that looks like supercuspidals at basic points, okay? Because maybe you anticipate what I'm getting to in a second, since I put two decompositions here, right? So let me come back to your question. And so we expect, so what's easy to see, by the way, is that there's a containment. So if you have something which is sort of spectrally in the irreducible locus, and in fact it's cuspidal, and conversely, if you have something that comes from Eisenstein series, its Farg-Schulze parameter is reducible. Maybe that's not so surprising. So there's some interplay between these two a priori, and what we expect, so conjecture, and so this was made by us and also independently by Ayuta Takaya. So these two. Well, yesterday, SOD stood for semi-orthogonal decomposition, so I guess OD stands for orthogonal decomposition. Agree. Always. Okay. And so now to answer your question fully, this means that D bun G cusp is supposed to be the supercuspidals whose Farg-Schulze parameter is supercuspidal, okay? And so we're avoiding the dreaded mixed supercuspidals, right? Other questions?
So easy means unconditional for G?
Yes, for any G. Okay. So theorem. So if G is well understood, the two orthogonal decompositions agree. Okay. And let me give a very brief sketch. So what are we trying to prove? We're trying to prove that, well, there's two ways to think about it. If you're a cuspidal sheaf in this sense, then you have irreducible parameter, or dually, if you have reducible parameter, then you come from an Eisenstein series, okay? And it turns out the second one is easier to prove, right? Because remember, we're giving ourselves all this access to classical local Langlands, right? So if I'm at a non-basic point, I'm already in the image of some Eisenstein series no matter what, that's easy. If I'm at a basic point, and I'm not supercuspidal, I'm also in the image of Eisenstein series, because those are induced. So now I have to figure out what's happening with supercuspidals at basic points. And here there's a dichotomy, right? The true L parameter may be supercuspidal, or it may not, right? If the true L parameter is supercuspidal, then by our hypothesis, that everything's compatible with Farag-Schulze, that means the Farag-Schulze parameter is irreducible, right? So there's nothing to do there. And so the key thing to do, to check, is somehow the only complementary case, namely that is that for any basic B and supercuspidal GB of F Europe sigma such that the true L parameter that we were giving ourselves by hypothesis, such that this has non-trivial monodromy. So this is tantamount to saying that this sigma lies in a mixed packet, right? This is one of the hypotheses that we put on our classical LLC. If you have a discrete parameter, then the packets have to contain something that's discrete but not supercuspidal, okay? But they can still contain supercuspidals. So we have to check that this, then IB lower shriek sigma actually lies in D bun I's.
How are sigma and pi related?
Pi should be sigma, that's how. Thanks. Yeah. This is the true L parameter of sigma. Sorry about that. Much less confusing. Okay? This looks perhaps insane at first glance, right? Because sigma is a supercuspidal representation of some basic, so inner form of the group. And I'm claiming that if its true parameter has monodromy, it's actually going to be in the image of one of these I's functors, right? So classically, this doesn't make any sense at all if you're just thinking about parabolic inductions. But I's functors are weird enough that this actually works, okay? And the way that we do this is that we use, so to do this, we use the Hecke stability of this cusp I's decomposition, plus a rather severe theorem from this paper I wrote with Jared and Tasho to check that there exists a non-zero map from some Hecke translate of the thing that we're looking at, so IB shriek sigma, to some IB primed shriek, let's say pi, where pi is not supercuspidal. The rough idea is that this sigma, because it's supercuspidal, but its parameter has monodromy, its total packet will contain things that aren't supercuspidal, and the Hecke operators move you around enough in the total packet that you can actually check that such a map exists, okay? And this is the only place that we use the endoscopic character identities for discrete series packets, okay? So this uses the endoscopic character identities, which would be nice if we didn't need these, but right now we do. Okay, questions about this sketch? Yeah? The character identities are an axiom in HKW, and here they're in the dot, dot, dot.
The way you use them in the proof?
Yeah. There's a theorem in HKW that says, like, if you have a classical local Langlands thing with good control over all these character identities, and you hit something with a Hecke operator, then up to some controlled ambiguity, you can say what you get. And we're using that. But we really need this hypothesis. Okay? Other questions?
So B prime is some auxiliary basic element?
B prime is some random other basic element, and pi is some random other element in the total Vogan packet, or whatever you want to call it, BG basic packet for this parameter phi sigma. Yeah.
Is there any representation theoretic explanation of this map?
No. Hecke operators are really mysterious and hard to work with. And
Why the sad face?
say again?
Why the sad face?
Oh, because I wish there was an approach that didn't require all this heavy machinery. Endoscopic character identities are highly non-trivial to check, right, for any given LLC. They're somehow the hard part, the hardest part, it might be fair to say. Okay. Yeah, okay, so strictly speaking, this will be in our second paper, but it's like the student exercise. This is not the hard part of that paper. Yeah. Okay, in the interest of time, maybe I keep going. So this is the leverage that we'll need to now execute, I think, step 2. Okay, so back to the functors. Oops, that's not what I want. Where is it, Sagu? Which button do I click? Ah, thanks. No, not that. The pencil. Oh, great. Makes logical sense. Okay. Okay, so to control CSI, we will use this together with this hypothesis, which already came up. I think Lucas called it eyes, and so I want to formulate this carefully. Okay, so for P fixed, we have this eyes P minus functors. This will go from sheaves on bun M to sheaves on bun G, okay? And then on the spectral side, there's actually 2 very closely related variants of eyes that you can work with. So there's this eyes P spec, which came up already in several talks. This was defined on INCO, and I want to just point out you can tweak this a little bit by remembering that pullback, push forward also makes sense on QCO. And so I'm going to label this CRS for course. And so this goes from D bun M to D bun G. And this goes from QCO par M, QCO par G. Okay, it preserves CO, and then the true Eisenstein thing is just the end extension of the restriction of this to co-QC. Okay, so they're very, very closely related. Okay, and so here's eyes. So this is the assumption that for any standard parabolic P in G, there exists a commutativity datum for the diagram, which looks like so. So here I have D bun M, compact sheaves. This maps by eyes P minus streak to D bun G, compact sheaves. This maps by C, Whittaker datum for the Levy to QCO par M. And this maps by coarse spectral eyes to QCO par G. And this is C psi, so for the group G. And did I make any typos? No, this is correct. Okay. Some comments on this. There's not an obvious natural transformation handed to you by life. I mean, constructing a natural transformation is part of the issue of actually proving that there is a commutativity datum for this diagram. Okay. The appearance of the opposite parabolic is, again, related to the normalization of class field theory that we choose. You could change your worldview or fly south of the equator and then not put a, opposite. It's your call. Do what you want. The appearance of compact objects on the left is a slight subtlety. Okay, you might find this weird. This has to do with the fact that C psi is not quite the dual functor of A psi, but it's the adjoint. And somehow what you really want to prove is a statement about the dual functor of A psi, and that turns out to be almost C psi, and it agrees with C psi on compact objects. So in the paper, we label this guy C psi superscript CTS, but this is just a technical nuisance. Okay, so don't worry about this. Any other comments I want to make? Right, as we've said several times, this should be provable. So the analog in classical geometric Langlands is well known in some sense, and there's multiple proofs in the literature. And I think to first approximation, it's reasonable to think these proofs will adapt. So this is ongoing joint work with Linus and Lucas, okay? And for GL2, it's already been announced by Linus and Naoki. Okay, any questions about this hypothesis? So when I say eyes, I mean I'm giving myself this giant hammer, okay?
Why have you labeled with course? Is there a non-course version of
Yeah. There's a non-course one on INTCO. The course one is on QCO.
Oh, that's all. Oh, okay. You're just labeling it because it's
Yeah. But on co-QC, it's the same functor. It's another one of these stupid fiddly things, QCO versus INCO. Yeah. But this statement is unconditional, right? Because L doesn't make sense a priori, but C does. Okay, so this hypothesis at least can be formulated by only talking about functors that we know about unconditionally. Other questions? Okay, so now here comes the first theorem. So assume that G is well understood. And let me also give myself this.
Sorry, so you said that this hypothesis is now proved for some special cases and the
So-
special case is
Expected, I would say. Yeah, and this should be, like, proving this has nothing to do with classical local Langlands. This is a lot of, like, geometry and sheaf theory, blah, blah, manipulations, but, like, you don't need any classical input. The arguments are just some checking that 1,000 diagrams exist and commute somehow. Okay. Okay, so let me go back to the narrative. So let me assume G is well understood and give myself this hypothesis. I's, okay. So then C psi restricts to a functor, which I also call C psi, of course, from compact sheaves on bun G. A priori, this would just be a random, enormous quasi-coherent sheaf, but in fact, it lands in co-QC. Part G, okay? And once you have this, then you can define the Langlands functor, L psi, now from all sheaves on bun G to all of INTCO by IND extending. This only works if you know this finiteness property of C psi. Okay? Questions about this statement before I sketch the proof? There's a finiteness property of C psi. If you feed in something compact, you get something in co-QC. That's what it says. Okay? So proof. So let me fix some A in D bun G compact. So now I'm going to use everything I already discussed. We have these two semi-orthogonal decompositions, right? They're actually the same. So this A decomposes into some A cusp, direct some AIs. Lo and behold, that's the same as hitting A with this idempotent E ear A, or this other complementary idempotent E red A. Of course, these are summands of a compact thing, so these are both still compact, okay? So then a direct calculation shows that on the cuspidal part, so C psi of E ear A, this is in co-QC. And here I'll write the whole parameter stack, but almost tautologically it's clear it's supported on the irreducible part of part G. And that's why you can do this, okay? The irreducible part of the parameter stack is very, very simple. Every component is a gerb over a torus, okay? And it's very straightforward to somehow give a checkable criterion for when a sheaf there is coherent. And it turns out you can write down and apply such a criterion, okay? So this part is unconditional for any group. If you have a sheaf, a compact sheaf A, which is killed by E red, C psi will send it to something in co-QC. So the hard part is the complementary part, the Eisenstein part, okay? And so now we know by the fact that these decompositions agree that E red A, this is generated under finite colims and retracts by things of the form I's P minus shriek B. So here P is proper standard. This is some MU. And B is a compact sheaf on bun M. Okay? Now what happens if I try to compute C psi on a sheaf like this? Yeah, B. Well, I'm giving myself this giant sledgehammer, right? I can commute C psi with an I's functor, literally by hypothesis. So this will be I's P spec course C psi M B, right? And now we win because this is in co-QC by induction, since the levy got smaller. So induction on the semi-simple rank, if you want to be precise. And this preserves co-QC. That's the sketch. Any questions? So let me just emphasize one more thing. Even if I gave myself eyes alone, then I would be able to control C psi on this part of A and on this part of A, okay? And without well-understoodness, you don't know that those two parts give you everything. So well-understoodness lets me match this with this and this with this, and you really need that, okay? Any questions?
Say more about a direct calculation shows.
Yeah, so a toy model would be like, if the group is semi-simple, then what does a component of the irreducible locus look like? It looks like point modulo of finite group, right? And for something there to be coherent, it's enough that if you tensor it with any irrep of that finite group and take global sections, you get something finite dimensional, right? But tensoring with an irrep is like applying a Heck operator, and then taking global sections is like Hamming from Whittaker. And you can turn that into an actual argument. Because Heck operators preserve compact things, and Hams from Whittaker to a compact thing is like finitely generated over the Bernstein center, blah, blah, blah. So that part works for any group. Other questions?
You needed the well-understoodness to know that C psi preserves colimits so that you could do this index.
I actually didn't use that anywhere. Oh, sorry. I'd used it here, of course.
Sorry, where? To define L psi by index.
Okay, maybe that's an even more primitive like layer in my brain. So C psi kind of sucks if it doesn't preserve colimits, okay? And then you should argue with this other thing labeled C psi continuous, which is almost the same functor. But don't worry about this. I mean, if G wasn't well understood, then I couldn't do any of this anyway. So, yeah. Okay, other questions?
That is, it wouldn't land in co.
Yeah, I'm using both conditions here. Really need both conditions. Okay? Okay, so by this argument, we at least have access to this functor L psi. I don't really have time for this, but in the paper, we kind of wrote a very careful narrative explaining why, if you believe in the weakest form of CLLC, this is the only functor that you are allowed to use, okay? So some soft assumptions on what CLLC should look like force this functor on you, okay? This is the only game in town. It's not some sort of random candidate that we cooked up, but I don't want to go through that in detail. Okay, so what do we know? And so some facts at this point, just by construction. So this L psi, this is colimit preserving. It's QCO, RG, linear, it preserves compact objects, and it's compatible. So I'll say a few words about some of these. It itself is compatible with Eisenstein series. What else do I want to say? Oh, right, and it's also compatible with the central grading. Okay, let me say 2 sentences or 2 words about each of these. It's colimit preserving because it was the end completion of something else. Nothing to check there. It's QCO par G linear because C psi is perf par G linear always, and then we end extend. So that's not hard. It preserves compacts exactly because of the theorem we just proved on compact objects. It is just C psi going from compacts to co-QC. It's compatible with I's because we assumed that it's C psi is, and then you can carefully end complete that statement, okay? So that's a formal consequence of what we already gave ourselves. And again, compatibility with the central grading follows from the same statement for C psi, which follows from the same statement for A psi, which follows from a very, very general fact about the spectral action, which for instance is something you can find in Konrad Zoe's master's thesis. Okay? Questions about what we know so far?
C psi is perf par G linear just because A psi was?
Yeah, that's always true.
It just falls from a junction?
Yeah, it just follows from a junction and the fact that, like, you know, such and such is dualizable. Yeah, yeah. Other questions? But let me also draw one diagram that might help clarify. Get out of here, Siri. Because we have 2 functors now out of Bungie, and you might wonder how they're related. And it took me maybe 3 years to not be confused about this whole difference of INTCO versus QCO. Okay? So C psi does this, right? It goes from D of bun G to QCO. This L psi that we just constructed does this. Goes from D of bun G to INTCO. It turns out there's a vertical arrow here, which is just part of some very, very general theory. Because what is INTCO? It's formal inductive systems of things in co-QC, right? But QCO has all co-limits. So there's an arrow here which morally takes a formal inductive system to its actual co-limit, right? And this annihilates things. And we discussed this a little bit in the Q&A yesterday, right? There was this crazy colim L2n shifted by 2n that lives in INTCO and dies under this map, okay? So the difference between these two functors is not so big, right? And there's an implicit claim here that this triangle commutes. So L not only stands for Langlands, you can also think it stands for lift. We've artfully lifted C psi along this vertical arrow to get the correct functor. Okay? Questions about this? All right. That's what I want to say about L. Now, we come to our next friend. So since L psi is colimit preserving, it has a right adjoint, which I very creatively denote R psi. So this will go from INTCO R G to D of bun G. Okay. This is just the infinity categorical adjoint functor theorem, which is one of those swords that you should learn how to wield 8 times a day. It's very fun.
So CISA is
Yeah.
colimit preserving, is it?
Yes,
But somehow you want the source category to be INCO, not QCO.
target category.
Yeah, well, yeah.
Yes.
For the joint.
Yeah. You need INCO to appear. You know INCO has to appear. So C psi is clearly wrong, but you tweak it a little bit, okay? And this is quite analogous to what happens in geometric Langlands, although it's actually already, even at this step, it's not the same. It turns out this vertical arrow is an equivalence on some bounded below parts for some T structure. And in their setting, they can prove that C psi sends compacts to stuff that's bounded below, so you can then lift it.
There's a vertical arrow too from QCO to INCO.
Yeah, you have to be careful with that one. Yeah, this diagram has a left adjoint where you have, okay, if L is an equivalence, then it's its own left adjoint up to inverting the arrow. And then you'd have A psi going from QCO, and you'd have this XC thing going from QCO to INCO. So again, this is explained very carefully in the paper as part of this narrative of like why L is forced on you. Okay. Right, so with our adjoint functor sword, we have this right adjoint. What can we say about it? So it is itself colimit preserving, if I can spell the word, colim. Because its left adjoint is L psi, and that preserves compacts, okay? So it's colimit preserving QCO par G. Linear, it's compatible with the central grading. These are all kind of soft properties based on what we did so far. It sends admissible sheaves on par G to ULA sheaves on bun G, so that's maybe a little more fun. So this has some finiteness property out of the box, okay? And is compatible with constant terms. And let me say what the compatibility is. And this is by passing to right adjoints in the compatibility of L with Eisenstein functors. So this says that CT P opposite lower star composed with R psi is equivalent to R for the Levy, R psi M composed with CT P spec. Okay. What else do I want to say?
So the fact that it says admissible to ULA comes from the fact that in your C-psi sends compacts to coherence.
Or that L psi sends compacts to coherence, exactly. Because it turns out that something on bun G is ULA if R-HOM from compact is a perfect complex of vector spaces for all compacts. And if you're R-humming towards R psi, well, R psi is a right adjoint, so you can rewrite it as R-hum from L psi of your compact towards the co-thing that you started with, right? L psi preserves compacts. And then then a definition of admissible sheaf just stares you in the face. Admissible sheaves were reverse engineered to be such that this is true, okay? Only later did we realize that they're the suave objects in the Indico formalism, okay? Okay, so this is all formal stuff from what we did so far. We also need a highly non-formal fact. This is maybe the hardest single theorem in the paper, at least in terms of how many threads converge in order to prove it. So theorem, R psi preserves compact objects. This is not at all obvious, right? It's a right adjoint. So why the heck should this be true? Okay? And so we use the following criteria, which I like quite a bit. So I'll label this as a proposition, maybe it's a proposition. So assume that G is well understood, but you actually don't need this, you need much less. So or just that the Farg-Schulze map G, or just that this has finite fibers for all B, or just that. Okay, so this is weaker than well understood. I already sketched to you why well understood implies this, but this passes well along central isogenies, unlike this more delicate set of conditions that you need to call something well understood. Okay. So then if I'm given some sheaf A on G, so this is compact, if and only if three conditions hold. And so one is that A has quasi-compact support. It's clear you need this in order for something to be compact, not quasi-compact supper. I guess I'm hungry. Support. Another is that A has quasi-compact spectral support. I'll explain this after I write it. Okay, what does that mean? So this ring ZG spec, you should think this is a lot like the Bernstein center. It has a huge boatload of primitive idempotents in it corresponding to connected components of the parameter stack, right? I can hit a sheaf on Bun-G with any of these idempotents. Having quasi-compact spectral support means that all but finitely many of these idempotents kill the sheaf, okay? So the map from spectral Bernstein variety ring to endomorphism of the sheaf factors over finitely many components, okay? And three is that for all B compact sheaf on Bun-G, our hom BA is a bounded complex with cohomologies finitely generated as modules over ZG spec. And now you might be starting to sense some similarity with things that we discussed yesterday. Okay? Can everyone parse what I wrote here? Are there any questions about this proposition? Let me say a few words about how you prove this. I don't want to actually write the proof out, but it's not very unpleasant to prove this. So compact sheaves have quasi-compact support, so you need that hypothesis. Compact sheaves also have quasi-compact spectral support, otherwise you'd get some infinite direct sum decomposition by these idempotents into infinitely many pieces, and then it couldn't be compact. The last part is something you can convince yourself must be true by thinking about Bernstein theory. So the analog of part 3 for like one stratum of Bun-G, like if I have two compact smooth representations, and I compute R-hums from one to the other, this is a finitely generated, a bounded complex, and its cohomologies are finitely generated over the Bernstein center. So this is a very, very classic and fundamental theorem of Bernstein, okay? And morally, this says something like these endomorphisms of progenerators are, despite being non-commutative rings, they're regular and Noetherian somehow, okay? So this is some thing you can reverse engineer, and then you actually prove that these conditions imply compactness, okay? And this uses Bernstein theory in a fundamental way, and I don't want to sketch the proof in detail. Are there questions about the statement, though?
So you're using this finite fibers
I'm using it to know that for any connected component of the parameter stack and any B, there's only finitely many Bernstein blocks that live over that component. Yeah. But that's equivalent to imposing finite fibers, actually. Other questions?
So this criteria is a bit self-referential. In part 3, you are quantifying overall compact objects.
Yeah, but how is it? It's not self-referential. I'm probing my random sheaf A by homming from compact sheaves. Yeah. You'll see how we use it in just a second, and then you'll see the power of it. Other questions before we apply this thing? Okay, so let's apply this. Apply this. In the case where A is this right adjoint R psi F, so F is in co-QC of par G. Okay. So I have to check all three of these. Let's do the easiest one first. So I claim it's trivial that 2 holds because F itself is supported on finitely many connected components of the parameter stack, right? Those components will tell you which idempotence won't kill it when you apply this functor R, because R is Q collinear, okay? So 2 is, dare I say, trivial. 3 is super interesting, and we'll use everything we did in lectures 2 and 3. So let me see what happens if I R hom from a random compact B towards this guy, R psi F. Well, R is a right adjoint, so I may as well rewrite this as R hom L psi B F. Where does this live? Remember, L preserve compacts, B is compact, so this lives in co-QC. Par G. That's also where F lives, right? This L psi B and this F are completely random. The only thing you know about them is they live in co-QC. And guess what we proved yesterday? If I R hom 2 random things in co-QC, then it's a bounded complex, and its cohomologies are finitely generated over ZG spec, okay? And so now we conclude by the hard work in lectures 2 and 3. Okay, this is why we put so much effort into proving this spectral version of Bernstein's finiteness theorem, okay, is to use this criterion. Questions about this deduction before I discuss the first of these 3 things, which I didn't do yet?
The L psi is really C psi.
Yeah, this is something you can keep in mind. On compact objects, there's no difference between L and C, right? But psychologically, L is the left adjoint of R, so it's easier mentally if I write L here, right? But you should just think it's C if you want. Other questions? Okay, so it remains to check that the first condition here holds, that this R psi of F has quasi-compact support, okay? And this is the maybe most interesting one. So what does this mean? I need to show that if I take its stalk at some random B, then for all but finitely many B, the stalk is identically 0, right? So I want that IB upper star. And for reasons, let me put some other incantation here. I want to know that this is equal to 0 for all but finitely many B, okay? So it means to have quasi-compact support. So it's clear, and I'll say why, that the stalk at basic B is 0 for all but finitely many basic elements.
Does it say after IB over star?
REN, renormalized. So usual stalks take you from sheaves to like complexes of smooth GB reps, right? This superscript mandates that you twist it by some shifted half power of a norm character, okay? It's analogous to doing naive parabolic induction and restriction versus the normalized ones, which are morally correct.
But that wouldn't change its zeroness or non-zero.
No, of course not, of course not. But I'll use an identity in a second, which is ugly if you don't put this superscript, okay? Whenever you're moving between bungee and a stratum, you should always use these renormalized functors, okay? They're better in about 10 different ways. Right, so why is it clear that at basic points we're fine? That's okay because R is compatible with the central grading, right? So F, when you decompose it by the central grading, will only have finitely many non-zero isotypic parts, right? Each of those will correspond to the restriction of R psi f to a unique connected component of bun G, right? And connected components are indexed by basic Bs, right? And so only those basic Bs are the ones where the stalk could possibly be non-zero, so that's fine. But now we have to think about the non-basic Bs. So for a non-basic B, let me let P, I'm a little more tedious with my notation than people were yesterday, so let this be the parabolic of its Newton point. And let chi be this character of Galois invariant center of Levy of this. So we actually saw this yesterday, just in slightly different notation, right? So there's actually a theorem of Kottwitz that says that elements of BG are in bijection with pairs where you have a standard parabolic and a basic thing in its levy, whose Newton point has the property that its dynamic parabolic is exactly the parabolic you started with, okay? You should think that for GLN, this is analogous to drawing one of these polygons, and then each time you have a line segment, that gives you some GL subscript whatever, and each time there's a change of angle, that gives you a new GL whatever, and each of those pieces is just a straight line, so that'll give you a basic thing in that GL whatever. And the product of all those GL whatevers is a levy, okay? So up to some notation, we already saw this in Alex and Terhisa's talks, Alexander, excuse me. And so then, how am I going to control these stalks? Well, we saw yesterday that push forwards are really fragments of Eisenstein series. It turns out that stalks dually are fragments of constant terms. And so we know that there's an equality of the form IB upper star renormalized equals similar, but now I'm doing it on bun of a levy. Upper star, constant term, PB upper star. Okay. And so this is some soft thing that holds in general. This is proved in much more general variants in this paper with Linus and Peter that I already alluded to. Okay. And so let's think about the kind of sheaf that we're trying to analyze. I want to apply this to this R psi of some f, right? So on the right, I'll get a stalk for some levy of a constant term of R psi, right? And we already saw that R psi is compatible with constant terms. Okay, now I'm going to exploit that. So this implies that IB upper star renormalized R psi f. This is a stalk of the functor R psi. Now for this dynamic levy, B. Here I will have a constant term functor, but on the spectral side, because of this compatibility, PB spec. And in my worldview, there's a minus sign here. F. Okay. So I did several manipulations here, and I didn't write them all out, but the idea is that in the first thing I wrote here, on the right-hand side, you stick in R psi of f, because that's what we want to know the stalk of on the left. And then you have a constant term of R psi, so you rewrite that as R psi on a levy of a constant term. And finally, why am I looking at a graded piece? That's because this B that I'm taking the stalk at, right, this lives in a connected component of bun G, right? On the levy, it will also live in a connected component. That connected component will be singled out by this character. So by compatibility with the central grading, that's the only part of CT that will contribute to this stalk. Everything else will just be irrelevant, okay?
Just to make sure, I guess here, MB is equal to GB.
What?
Like the fullback by IB renormalized, isn't it like goes to
So GB is an inner form of M squiggly B. Yeah. I prefer to put these squiggles so that it doesn't look like MB is like a B twist of M. Yeah. Other questions?
I guess the previous question is asking where this equality takes place, right? It takes place in representations of
Thank you. Okay. So this is in rep smooth of GB of F, which is, okay, just hold your breath. Okay, so the bottom thing looks horrible, but has the advantage that B is basic in M subscript squiggly B, okay? So GB is an inner form of this thing, right? And again, from the point of view of this levy, this is a basic point in Bun subscript M subscript squiggly around B, okay? All right, we're almost done, I hope.
So could you say again why for basic B is easy?
Yeah, so for basic B, you know that basic Bs are indexed by connected components, right? And those on the other side correspond to the central grading of F itself. But F is coherent, so all but finitely many graded summands of it will be 0. Right? F has this chi decomposition. And like if there is a basic stalk at some basic point, it must come from the associated like chi B summand of F. And all but finitely many of those are 0. Yeah. Okay. Oh, but okay, so now we're nearly done. So, but we saw yesterday. That CTP, yeah, CTP spec minus chi of a fixed thing. Remember, F is fixed throughout this. This is 0 for almost all P. And now, because there's a minus sign upstairs, I have to put the word anti-dominant. Almost all P anti-dominant chi, okay? And so and this was the sort of part 2 of this hard theorem that we proved about finiteness of constant terms, okay? That if P is fixed, then for all but finitely many dominant superscripts here, it's 0, okay? Because there's a minus sign, I have to say anti-dominant, but just take a deep breath. And it turns out the assignment that sends B to this pair of this parabolic conjugated to be standard and chi B is injective. And this is always P. B, I hope my sign here, this is always dominant. Anti. Okay, there's some sign here that you have to be careful about, but I sweated very hard over this, and I think it's correct in the paper at least. So put anti in parentheses. Check it yourself. We win. Okay. Questions about this? The point is that as you vary over non-basic B, only finitely many of these P's can appear, these dynamic parabolics. And for each of them, the chi B that appears will be dominant, okay? And this map is injective. So the fact that for any fixed P, all but finitely many of these graded summands of the constant term vanish is exactly what lets you conclude, okay? Questions about this sketch? Okay, I have maybe 30 seconds, so let me say, just as a preview of where we're going. And this was already hinted in lecture 1. This R psi, let me just recap, okay? How did we get R psi? We started with A. We proved that it's not too bad. We passed to C by taking a right adjoint. We proved with a bit more effort that that's not too bad. We renormalized by restricting to compacts and changing the target and incompleting, right? And then we passed to another right adjoint. So we've done so many steps to get from A psi to where we are now. How the heck could you ever try to control this R psi, right? It's like completely inaccessible to human beings, okay? And so a preview of what's going to happen next, let's say preview of tomorrow. And this will be maybe the fundamental source of control of this R psi, which is very inexplicit. We'll prove that although this is a little bit hard to access in general, if you restrict it to co-par-G fin, which is this slightly thin subcategory of co that nevertheless is robust enough to kind of control everything, here you can give a formula, and this is this functor that Lucas called T psi. And this is pretty explicit. Okay? And so tomorrow you'll see this and how to think about this and the power of this kind of identity. And from there, we can move towards our goal of actually proving that L and R are equivalences of categories. And I think I will stop there. Sorry for going 1 minute over.